Hi, so welcome to week 7 of our class Combinatorics 2. And so today what we will do is we talk about non-homogeneous recurrence relations. So we've seen the homogeneous case, now we talk about the non-homogeneous case and we'll find out what this means and how to solve it. And then at the very end we'll also talk about something, the approach which is called like the approach via generating functions. Okay, and so the book really focuses on this case, so on this linear second order recurrence relation. And here, this is now non-homogeneous because we allow any kind of function on the right which depends on n. So something more complicated, a more complicated expression on the right. And so if it's called homogeneous if there's a 0 here, if not then it's non-homogeneous. So how do you solve this? And so again, this is 10.3, 10.4 in the book. So I kind of ordered it in like as a 3-step process. So the first step is whatever is on the right, you plug in a 0. Just plug in a 0. So forget about this and write in the 0. And then what you get is the homogeneous system. You get the homogeneous recurrence relation. And we know how to solve this. This is what we learned last time. So you find the general solution of this homogeneous recurrence relation. So important thing here is this is really like the general one, meaning you don't think about the initial conditions yet. So there will still be constants in there, which is completely fine. Don't try to specify them here. It will be very general. There will be constants in there. So think about like a1 times r1 to the n plus a2 r times r2 to the n, these kind of things. That's what you get here, and you call this an with an h up there to h stands for homogeneous. Now the second step, so the first one is usually very easy because we know how to do this. The second one, using this approach, is guessing, which is something you know doesn't sound very scientific. So what you do is you just need one solution. So you forget about anything more complicated. You really just want to have like one solution. You want to have an idea about intuition, how to come up with one little solution of this non-homogeneous system. So this non-homogeneous recurrence relation. And so that's what you do. You guess one particular solution. You write this as a and with a p. P stands for particular. Okay, so if you do that, we will see how this works. So what you do is we have an idea how it looks like. And of course, there will be still some constants in there. You have a rough idea how it should look like. So what you should do is you should check whether your guess is really right by plugging this into the non-homogeneous recurrence relation. And once you plug it in there, you have to solve for all these constants floating around, and you have to specify them. Okay, and so you will find out, it is possible, your guess was right. You will find some constant such that at the end you come up with a very specific, without any constants anymore, some very specific solution, right, which you know this solves this recurrence relation. But you want to have a general solution. You don't want to just have one solution. And so what you do is now, again, this should be familiar to people doing, knowing about linear differential equations. You take a homogeneous general solution and add the one particular solution, and then what you will get is a general solution of the non-homogeneous recurrence relation. So on the right, every solution of that non-homogeneous recurrence relation will look like this. It will be one particular solution plus the general homogeneous solution. Remember, there are still some constants in here, and so for these choice of these constants, we claim we can choose some of these constants so that they will be now satisfy the initial conditions. So if you choose the right constants here, the right side here will satisfy the non-homogeneous recurrence relation and the initial conditions, and so it will be equal to an. And so you set this up like this, you plug in the initial conditions and solve for the last remaining constants in here and specify them. And then you will have solved the recurrence relation with initial conditions. Okay, So let's look at an example. And we'll do a very easy example. So please look at the book where we have the more complicated ones, the ones which are on the exams. But let's look at one easier example. So one of order 1. But the idea, everything is the same. And so here's the one I want to look at. Very simple one. So a very simple reconciliation. an minus 1 has to be equal to n minus 1. And we only have one initial condition because this is of order 1. You only need a0. Once you know a0, you know what a1 is. Once you know 1, you know what a2 is. So we only need 1. But generally, as you've seen before, we're really talking about order 2. But I really do this example because here I can really do this explicitly. Otherwise, it gets so much more involved. Okay, so let's do the first step. First step is to find the general homogeneous solution. So you plug in a 0 here, so an is equal to 0. Well, this just means an is equal to an minus 1. We don't even have to do anything. It just means everything is just the same. So in this case, what will be the answer? Well, it will just be a0. And so instead of so in other words, it will just be a constant. A of h will just be a constant. If you have a constant, constant minus constant, certainly satisfies this. This is the solution. A into h is equal to a constant. Now, in general, of course, usually what you will get is something like this. Maybe a1. Yeah, why not? Let's call it c1. A1 times some number r1 to the n plus a2 times r2 to the n. Something like this is what you usually get, or a2 times n times r2 to the n. We've seen all these three cases, remember last time. So it will look like something like this. In any case, there will be some constants here. In this case here, which is a very simple case, we just have a constant. Okay? So you solve the homogeneous recurrence relation, you get something here. So we know this is a very easy step. You only have to solve the characteristic equation. Essentially, that's it. And you have to know about the three cases. Okay, now the important thing is do not plug in the initial conditions yet. Don't try to specify this constant right here. Even in some cases, it actually doesn't matter, as in this, I know, quite stupid example. In most cases, it will matter. It will be wrong. If you already now try to plug in a 0 here, then and try to fix that constant, in most cases, it will be wrong. Don't do it. Wait for the very, very last moment. That's a typical mistake on the exam. Okay, so second step. Now this is a step I really want to talk about. So you have to guess. To guess one particular solution. How do you do that? Well, what you have to do is you have to look to f of n. F of n was the right side. In this case, it's n minus 1. This really determines how it's going to look like. This is what you have to look at. What you see here is you see a polynomial of degree 1. So a good choice is that it will be a polynomial of degree 1 with some constants you don't really know yet. Let's call them a times n plus b. That's a very good guess. So let's just check this. So then now the second step, you have to find out these constants. You plug it in. So what will happen? So we get a n plus b minus a times n minus 1 plus b should be equal to, well, it just should be equal to n minus 1. So let's simplify the left side. an minus an cancels, plus b minus b cancels, and we will get plus a. So the left side is just simply equal to a. And you wouldn't believe so, this should be true for all n greater equal than 1. Now you wouldn't believe how many exams I've already seen where people just say, okay, now we go on. Where is the mistake? This should be true for all n greater or equal than 1. So you have different values here, but you have only one value on the left. It's a constant. It has to be a constant. So this doesn't work. So this tells you the guess was wrong. Now how can you make up? So do second guessing. And this is something I will tell you how to do. So here the idea is the following. And why not already tell you now? So here what we have is, the problem is the homogeneous solution. You do not want the homogeneous solution to somehow interfere with your particular solution, because homogeneous solution, once you plug that in, you will always get a 0 on the right side. It's not what you want. So in this case, you have an, or maybe that is not the right way to say it. The trouble is, if you get 0 on the right side, that constant doesn't matter. You lose the choice of freedom. In any case, what you have to do is you look at these terms, a times n, that's a good term, that's nothing to do with a constant, but b, it's just a constant. We also have a constant here. We don't want that. So what you do is, you do second guessing, you take this one and multiply everything through by n. So this is a new guess. It's just to multiply this through by n. Okay, and so this is a n squared plus bn. Again now, you have to plug this in. You have to check it. You have to specify it. Right? You want to specify these constants. So again, let's do the same thing. You plug this in there. A n squared plus bn minus a n minus 1. Now here you have to be really careful not to make any mistakes here. So this should be equal to n minus 1. If I didn't make any mistake. And so let's simplify the left side. Okay, let's just write down. I already did this. So on the left side, so this should be equal to n minus 1. 4. And so what do we see? We get 2an minus a plus b equal to n minus 1 for all n greater than 1. That's the condition you want to have. Okay, and so for which constants does this work out? Well, this is a polynomial. The polynomials are equal if the coefficients are the same. So 2a should be equal to 1, and this stuff here should be equal to minus 1. Right, so that the constant, the factor in front of n should be the same to that, and that factor should be the same to that. Of course, you can bring everything on the one side, also possible. And so what you will see is, if you solve this, we get that a is equal to 1/2. And if you plug that in, minus 1/2, bring it on the other side, you will see that b has to be minus 1/2. Okay, and so what did you just see? Is that a and p, so the particular solution is a1, which was 1/2 n squared plus b, which in that case was actually n minus 1/2 n. And so this is a specific particular solution of a non-homogeneous Recurrence relation. And so finally, step 3. Is to just put it together. We have a homogeneous solution. So a n should now be thought of a n of h, the general homogeneous solution, plus the particular solution. So in this case, the homogeneous solution was just a constant, plus 1/2 n squared. N. And so we have one constant here left. In general, it might be, it's usually like 2 constants. If you have order 2, so you have 2 initial conditions, so there will be 2 constants here. And now in our case, you only had 1 initial condition, so now let's solve for that. That was n equals 0, a0 was 2. If you plug in now 0, this vanishes, you get that this is C has to be 2. And as said, if you have usually have two conditions, so you plug in A0 and A1. And so the answer will be 2 plus 1/2. So 1/2 n squared minus 1/2 n plus 2. Will be a solution now for all the n greater or equal than 0. And again, a word of caution. Only at the very end you plug in to solve for the initial conditions. You don't need them before. Namely, remember, if there would be something else here, maybe this would look like 1/2 n squared minus 1/2. And then you would plug in here, you would have to solve 2 equals c plus 1/2 or something. Then c wouldn't be 2, like in this case. And this would also have been what you got at the beginning, but maybe if it would have looked different, you would have gotten something else here. So the difficult part is to come up with a second guess. So how do you, or in other words, the first guess, how do you guess the particular solution? So let's look at this example. So we have a second order consolation as usual, and you have on the right side something which might be non-homogeneous. Now, first thing is you plug in the 0 here, you solve for homogeneous equation, recursion, and you get this general homogeneous solution. This is important in your guess. So you need this data and you need this. So the first guess only looks at the right side, and the second guess takes also into account what you had here. So here's now this big table. Let's go through it, and you will get an idea about how to do this. So the one is a very special case if you have like a sine function in there on the right side. So this is the right side. This is f of n. This is on the right side. Then a guess for the particular solution will be a linear combination of sine function and cosine function. So a sine n theta plus b cosine n theta. Okay, let's go to the cases which are more often occur. So for instance, the right side is just 3. What do you think of 3? Maybe it has something to do with 3 to the n. Shouldn't you be careful? Well, 3 is just a constant. So if you think about it as a constant, your guess is a constant, and in fact this is okay. So what about the right side is 3n squared? What do you think? Is it maybe a times n squared? No, you should think about this as being a polynomial of degree 2. So the general guess will be, the guess for the particular solution, an squared plus bn plus c. Now, 3 times 8 to the n. You should think about it as being a constant times exponential function 8 to the n. So this is a good guess would be a times 8 to the n. Now it might get a little more tricky. You have 3 to the n. Now 3 to the n, good guess would be of course a times 3 to the n. But careful, 3 to the n also occurs here. So what you do is you multiply through by n. So it's a times n times 3 to the n. Now we have 3 to the n plus 8 to the n. Now what you do is you look, whenever you have on the right side a sum, think about each summand extra. Do the guessing completely for the one part, for one summand, and then you do it for the other summand, and then at the end you add it up. So in this case, look at 3 to the n. You already know this is a times n times 3 to the n, 8 to the n. This is a times a to the n. So this is a times n times 3 to the n plus b times 8 to the n. Okay, maybe you have 3 to the n plus 7 to the n. In this case, 3 to the n gives you a times n times 3 to the n. What about 7 to the n? 7 to the n also occurs here. So constant times 7 to the n wouldn't work. So you need to multiply it by n, and so you would get this. Okay, let's look at the harder part. What about n times 3 to the n? So this is a little more complicated because what you should think about it is being it's a polynomial of degree 1 times 3 to the n. So the first guess always only looks at this, is polynomial of degree 1, general polynomial, so a n plus b times 3 to the n. So this is the first guess. But now you realize if you sum this out, you have a times n times 3 to the n, no problem, but you have b times 3 to the n also. This is a problem because this is just constant times 3 to the n, which you already had here. You don't want to have that, so what you do is you multiply through by n. Now sometimes, maybe we see later an example, you might even have to multiply by n squared. But if you multiply through by n, what you see, you get a times n squared 3 to the n plus b times n times 3 to the n, and none of this interferes in any way with what we had here. So this is good. What about n squared times 3 to the n? Well, first guess is this a quadratic polynomial. So what you should have is this one here. And now you look at this, and what you realize is this is okay, but c times 3 to the n is not okay, because this is just the order constant times 3 to the n, so you multiply through by n. Okay, so I hope you got the idea how to do this, but let's make it even more complicated. And let's look at a second example. Yeah. Here it is, namely, assume we have a situation that the homogeneous solution is this form. So maybe it comes from a double root, a1 3 to the n plus a2 n times 3 to the n. And now assume that on the right side you would have 3 to the n, and maybe you have n times 3 to the n. How do we come up with a guess, with the right guess? Okay, you have 3 to the n. This is constant times 3 to the n. It's not good. No good because, so the first guess was a times 3 to the n. No good because this is already here. So if you now multiply by n, better, but still bad, because n times 3 to the n is here. So you do n squared, and now you got the right thing. So this will work. So of course you have to check it. You have to plug it in and so forth and so for the constant, but that's something else. Now what about here? First guess, you look at it, see it's a linear polynomial, an plus, so it will be an plus b times 3 to the n. That's the first guess. Now there's a lot of trouble going on here. We have n times 3 to the n plus constant times 3 to the n, so that's not good, so you multiply by n. Now you have a n squared 3 to the n, which is good, but you also have plus b times n times 3 to the n, which is not good, so you have to multiply n squared. And now we get like quadratic times 3 to the n and cubic times 3 to the n and quadratic times 3 to the n. So this is good. Okay, so this is how you do this. And so look at these examples in the book and the table in there, and everything in here you can also find in there. Okay, so you probably don't, or maybe some of you don't like this guessing part. So there's an alternative way how you can solve these non-homogeneous recurrence relations. And that involves generating functions. So this is a different way how to do it. It's a little more technical, it's more sophisticated, but it also is much more systematic. So let's look at this example here. It's just of order 1, but we will see how generating functions come in here. So you should think about this recurrence relation as being like a series of infinitely many equations. So we have one for n equals 1, for n equals 2, and so forth. So what we want to get in here is the generating function. So recall what this is. So here it is. And so how do we get this in? The idea is that we essentially take these infinitely many equations, multiply them by the corresponding x to the n, and just sum them all up. So here's what I mean. Multiply the left side by x to the n and the right side by x to the n. And take it out. Okay. All right. And now we sum up all of these conditions. And so if you sum them up, we can take the sum in here, here, and in here. And the conditions go from n equals 1 to infinity. Because this is precisely the range that this equation holds. So this. Okay, so let's check. Okay. And now we are very close already to the generating function. You see, it just like immediately appears, namely here. The only thing is like this was missing the 0 and the 1 here was the difference. So this is equal to the generating function f of x. And do not, this is now very bad notation, I just realized. This f of x here, I just used it because we often denote this in the generating function. This has nothing to do with the right side of the recurrence relation, okay? Of course, it also turns up here, but don't, because we used f of n before, just forget about that, okay? All right, so f of x here now is that generating function, and now this is nearly the same minus a0. Okay, and if this would start from n equals 2, we would subtract minus, so we would write minus a0 and minus a1 times x. But in this case, this is just that. Okay, so look at this. Maybe we also see the generating function here. It looks a little bit strange. But now you see, like, these are different, n minus 1 and n. So what you do is you can take the x out. Okay, so just take the x out. So minus 3 times x to the n minus 1 now. And now just plug in the number. If you plug in n equals 1, we get a0 times x to the 0 plus next one, a1 times x to the 1, next one, plus a2 times x to 2. This is the generating function. And so on the left side now suddenly we only have things you all know. So now you see actually this is something which is different from before. Now we already have the a0 here. So we're allowed to, in this case, to plug this in, to replace this by f of x minus 1. Now what about this one? Here is now where you really need your knowledge on generating functions and your knowledge on how to recognize how to write this in a different form as a quotient of two polynomials. And you should actually know how to do this. If you do not, and you have to try to figure this out, because what is this sequence? Well, this is a sequence 1, 2, 3, 4, 5, and it's generating function. So, of course, it starts from 1, but of course, if you plug in 0, you can just actually start from 0 if you like. And so, it's the same thing, because, well, 0 times x to 0 is just 0, so you can just add it. You can start from 0 if you like. And now it's really the generating function of the sequence 0, 1, 2, 3, 4, 5, and so forth. And so you should be able to write this as a quotient. And so in this case, this is x divided by 1 minus x squared. And if you do, and definitely so look this up. Good exercise to do this again. And so here we see the limitations of this approach. The limitation is the following, that you really need to be able to express the right side in this form. And for that, you have to really you have to know something about this. And depending on this case, it's possible, but maybe in more complicated cases, it's much harder. But here it works out nicely. In many of the examples, all the exercise in the book, they actually work out nicely. And so what we do now is we look at the left side and the right side, and we just solve for f of x. So summing up, what I just had there was f of x minus 1 minus 3 times f of x equal to x divided by 1 minus x squared. And so let's just solve for f of x. What do we get? Well, it's not hard. Get this. Okay, so you just bring everything on one side, bring everything on the other side, divide by what is in front of f of x, and you will get this. Now comes something else. So in this approach, there has to be some more technique. I said it would be more technical. So far it was okay. But here you really need to simplify this. And so what you need is a technique you surely have seen before. This is partial fraction decomposition. So partial fraction decomposition tells you how to write this in a simpler form, namely as a sum of easier fractions. So let me write. So what it does is the following. It looks at these fractions, and what we have here is 1 minus 3x, and we have 1 minus x squared. And that means that technique tells you that it's possible to write this fraction as a sum of, as a linear combination of these fractions. This means like as some constant times this fraction, plus some constant times this fraction, plus some constant times this fraction. If you don't know about this, look it up. There's also a little bit about this in the book. And so essentially it all boils down to solving some equations, and once you get that, you get these constants here. And so finally, don't forget this one here, we have to add that one. Okay. So let's, we see we can get something here together. Let's simplify this. Okay, now we're here. All of this can actually always be done. So this works if you know about this technique. So we'll always point down to get something like this. Now, why is this very nice? So far it looks really like, oh my God, what am I doing here? Well, this is stuff we know. We know what we can write this as a sum again. Okay, 1 over 1 minus 3x, what is it? Well, it's like 1 over 1 minus x, but instead of x we have 3x, so it's 1 plus 3x squared plus 3 to the 3 times x to 3 and so forth. Here we have minus 1/4, 1 plus x squared and so forth. Here we have 1 over 1 minus x squared. Well, that is something, again, you should know. If you do not, please look it up. In this case, we get 1 plus 2x plus 3x squared okay, so 3x squared and so forth. And now we can summarize this all together because now we solved it. Let's do it here. We can now find out what an is. Because what did you compute? You computed f of x, which was a generating function. It was the sum n equals 0 to infinity an x to the n. So we just have to look at the coefficients of n, of x to the n. So in this case, you see this is just 7/4 times, 3 to the n. Okay, so for instance, the second coefficient here is 3 to the square. And now we have minus 1/4. Okay, here the coefficient is just always 1. So we just get 1. And finally, what's the coefficient here? Minus 1/2. Okay, the coefficient to the square is 3 to the, so it's always 1 more. So this is n plus 1. And that will be the answer. So we can simplify it a little bit more. And that will be the answer for n greater or equal than 0. And so now we see also here, this is something like you would probably get from a homogeneous solution. It's more from a particular solution. But in any case, what this tells you is, you get directly, just from reading, you can directly read it off the coefficients. There's no more thinking involved here. The main thinking part is, that's also a technique which is very algorithmic. The main thinking part here is to really recognize how to go back from here to the series. But that's something you should know how to do that. Okay, and so please look at following examples. 10.38 plus 10.39. All right, so please do some exercises and see you next week.